as our third theorem, Theorem 3, convergence of P series. So infinite series, the sum from 1 to infinity of 1 over n to the p, it converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. And so this should feel very, 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 very similar. This should feel just like the integral test, improper integrals, the p integrals. Very, very similar statement, very, very similar result here. And in fact, we're going to prove it by combining the p integral test together with the integral test from our previous theorem. So let's go ahead and do that. We have to break this into some cases. So once again, we're thinking about the sum from n from 1 to infinity of 1 over n to the p. So case 1 is if p is negative here, then this is really, p is less than or equal to 0, then the sum from n from 1 to infinity of n to the minus p, in this case, minus p, if p is negative, this is at least 0, and so limit as n goes to infinity of n to the minus p is not equal to 0. It's either equal to 1 if p is exactly equal to 0, or it's infinity otherwise. And so we already know from last section, if the limit as n goes to infinity of a sub n is not equal to 0, then the overall sum diverges. So now we've got that out of the way, we can think about, so let's assume that p is strictly positive. So now we're going to do this with the integral test, and we're going to think about f of x is 1 over x to the p. And so this is positive, continuous, and decreasing. So it's pretty easy to check that all of that stuff applies. So positive, decreasing, continuous. And f of x agrees with, f of n agrees with a sub n. So we can apply the integral test. So what's going on here? This is just the integral from 1 to infinity of 1 over x to the p dx. And we know this from our section on improper integrals. This is either equal to 1 over p minus 1 if p is greater or equal to 1, or it's infinity if p is less than or equal to 1. And so this means it diverges, and this means it converges. And so by the integral test, the behavior of the integral is exactly the same as the behavior of the series. So if p is at least 1, the integral converges, and so the infinite series converges. If p is less than or equal to 1, either or in this case where it diverges, or in this case the integral diverges, so by the integral test the series diverges, or in this case we just said that the series diverges. So that takes care of all of these cases here. So the infinite series, the sum from n from 1 to infinity of 1 over n to p, converges if p is at least 1, diverges if p is less than or equal to 1. It's exactly the same behavior as the integral from 1 to infinity of 1 over x to the p dx. Let's do a couple of quick applications of this. First off, I'll just note that the harmonic series is a simple case where p is equal to 1. So right here, we get that p is equal to 1 means that the series diverges. So hey, we already did an example of this. Two more examples. The sum from n from 1 to infinity of the cube root of n. So this is going to be p is 1/3. 1/3 is less than or equal to 1. So we conclude that this diverges. In this case down here, p is equal to 2, and 2 is at least 1. Sorry, not just at least 1, but strictly larger than 1. So this tells us that this infinite series converges. Now, it doesn't tell us at all what this is equal to. It tells us that it converges. Just as a little math anecdote here, the value of this is actually pi squared over 6. And it's very non-trivial to get that answer. It's due to the great mathematician Leonard Euler that he was able to show that this is pi squared over 6. This is not something that you need to know. This is the sort of thing that I usually teach when I teach Math 311 or Intro to Real Analysis course, an upper level course for math majors. Okay, so this is our P-series test here. Tells us when our P-series converge or diverge. To wrap this up, here's our second pre-class problem. Determine if these are convergent or divergent. Sum from n from 1 to infinity of 5 over n to the 0.97, and then 2 over n to the 1.001. Of course, those constants are just red herrings. You can move them outside the sum.